Imagine standing in the middle of a rainstorm where the rain passes straight through your body without getting you wet. No sound, no impact, no trace. That's essentially what neutrinos do. Every second, trillions of them pass through your head, your phone, your walls, even the entire planet, as if nothing were there. Neutrinos are often called ghost particles because they almost never interact with normal matter. They don't carry electric charge, they're incredibly light, and they're famously antisocial. Most particles bump into atoms, scatter, leave marks. Neutrinos? They slip through everything like whispers in a crowded room. Yet these ghosts are incredibly important. They're born in the most extreme places in the universe: exploding stars, nuclear reactors, black hole environments, and, most constantly, the core of our sun. Every neutrino coming from the sun is a direct message from its heart, sent straight to Earth at nearly the speed of light. Light itself takes tens of thousands of years to escape the sun's interior. Neutrinos escape immediately. That makes them something like live broadcasts from the sun's core, while sunlight is more like a delayed recording. The problem is obvious. How do you catch something that doesn't want to be caught? Trying to detect neutrinos on Earth is like trying to hear a pin drop during a rock concert. Cosmic rays, natural radiation, and random particle noise are constantly smashing into detectors. Neutrino signals are so faint they get completely drowned out. So scientists did something counterintuitive. They went 2 kilometers beneath the surface, inside an active nickel mine near Sudbury, Canada. This is SNOLAB, and it's not a normal laboratory. It's more like a bunker designed to escape the universe. Above it lies a massive shield of rock that blocks almost all cosmic radiation, turning the chaos of the surface world into near silence. At the heart of SNOLAB is SNO+, a detector that looks less like scientific equipment and more like a sci-fi artifact. Picture a giant transparent sphere, 12 meters wide, filled with hundreds of tons of a special glowing liquid. Surrounding it are about 9,000 ultra-sensitive light sensors, all pointed inward, all waiting. Think of SNO+ as a dark concert hall. The lights are off, the audience is silent, and everyone is waiting for a single match to be struck. When a particle interacts with the liquid, it creates a tiny flash of light. The sensors catch it. From that faint sparkle, scientists can reconstruct what happened, where it happened, and how energetic it was. Most of the time, nothing happens. And that's exactly what they want. Now comes the part that makes this discovery special. For decades, scientists believed that solar neutrinos should occasionally interact with a rare form of carbon called carbon-13. Not normal carbon, but a slightly heavier version that exists in small amounts in nature. If a neutrino hits carbon-13, it can transform it into nitrogen-13. That's not chemistry. That's nuclear alchemy. One atom quietly becoming another, triggered by a particle that barely exists. This reaction was predicted long ago, but never directly observed. It's like knowing a rare bird exists, but never managing to photograph it. The SNO+ detector finally caught it. Here's how they knew. When the neutrino strikes carbon-13, it creates a first flash of light. Then, about 10 minutes later, the newly formed nitrogen-13 decays and produces a second flash in almost the same spot. 2 flashes, same place, separated by time. Scientists call this a delayed coincidence, but you can think of it like hearing a doorbell ring, and then, 10 minutes later, the same door gently closing. Random noise doesn't behave like that. Only a very specific process does. Over more than 230 days of observation, scientists detected exactly the number of events theory predicted. Not dozens, not hundreds, just a handful, but enough to say, yes, this reaction is real. At first glance, detecting just a few events might sound underwhelming. But in neutrino physics, this is huge. This is the lowest energy observation ever made of neutrinos interacting with carbon-13. It's also the first direct measurement of how likely this specific interaction is to happen. Before this, scientists had equations and simulations. Now they have evidence. Think of it like finally testing a recipe instead of just reading it. The ingredients, the timing, the result, all confirmed. This matters because neutrinos are deeply tied to how stars work. They influence nuclear reactions, energy transport, and even the life cycles of stars. By understanding exactly how neutrinos interact with matter, scientists refine their models of the sun and other stars. It also matters for neutrino physics itself. Neutrinos are famous for breaking rules. They change identity as they travel. They barely have mass. They don't fit neatly into existing theories. Every new interaction we observe is like finding a new piece of a puzzle that refuses to behave. SNO+ stands on the shoulders of a giant. Its predecessor, the original Sudbury Neutrino Observatory, helped solve the solar neutrino problem and contributed to a Nobel Prize in Physics. That experiment showed that neutrinos change type on their journey from the sun to Earth. This new discovery doesn't shout. It doesn't explode. It whispers. But it proves something profound. Even the rarest interactions can be measured if you listen carefully enough, long enough, and deep enough. By watching a giant tank of liquid in near total silence, scientists caught ghost particles from the sun, quietly rewriting atomic identities. No drama, no spectacle, just patience, precision, and a few flashes of light in the dark. And with this new tool now confirmed, scientists can go hunting for even more elusive neutrino interactions, each one another message from the hidden machinery of the universe. Sometimes, the universe doesn't scream its secrets. Sometimes, it waits for you to go underground and listen. Deep underground, shielded from cosmic noise, scientists observed signals that confirm a long-predicted neutrino interaction. The result does not rely on large numbers, but on consistency between observation and theory. Each detected event represents a direct probe of nuclear processes occurring in the sun's core. By measuring this rare interaction, researchers have expanded the known ways neutrinos interact with matter. The experiment demonstrates the effectiveness of deep underground detectors for studying low-energy neutrinos. It also provides a new benchmark for testing models of neutrino behavior and nuclear structure. Although the signals were few, their statistical significance is strong. This measurement reduces uncertainty in how solar neutrinos interact with carbon-based materials. It confirms predictions that had remained unverified for decades. The SNO+ detector continues the scientific legacy of its predecessor with improved sensitivity. These findings support current models of stellar fusion and neutrino oscillations. They also open the possibility of observing additional rare neutrino processes in the future. Progress in neutrino physics depends on such precise and controlled measurements. This result marks an important step toward a more complete understanding of fundamental particles. Even the weakest interactions can yield powerful insights when observed with sufficient care.